Hello everyone, my name is Yuan from the School of Architecture at UIUC. This presentation is modeling and analysis of tripod-scissor deployable structures using measured assembly methods. Firstly, I would like to go through the main points of this presentation. The first part introduces a brief literature survey of scissor deployable structures. Then the basic design concept of using a measured assembly approach of the tripod-scissor unit will be discussed. Part 3 is the parametric modeling and analysis of 4 unit blocks. The parametric analysis focuses on 2 geometric factors, the segmental length and the kink angle. Lastly, a series of large-scale deployable forms were designed, including an expandable arch, dome, and a tetrahedron. Scissor-like elements is a popular type of deployable structures. The fundamental unit of this structure is shown here, which connects 2 members using an intermediate hinge, just like a scissor pair. The past studies have thoroughly examined the geometric and kinematic properties of scissor structures and developed 3 basic types of planar units, which are translational units, polar units, and angulated units. On the right side is another type of unit which has 3 members that are connected at the center. It was named as tripod-scissor unit in this study to distinguish from the traditional planar units. Actually, the tripod-scissor unit is the initial prototype of scissor-like element, which was designed by a Spanish architect Piñero in the 1960s. However, planar scissor units were much more popular in the research and practice because the design and analysis of tripod-scissor units are very complicated. Here are some other studies about this type of units. So we are looking for new geometric design and assembly methods. This diagram shows the way how units are connected. On the left, 2 scissor units are connected linearly, namely 2 units are translational symmetric. In this case, we know that the structure assembly has this geometric condition, and to achieve the fully folded configuration, the following relationship must be satisfied. A, B, and C, D are the segmental lengths of the structure. Part B shows the conventional assembly of 2 tripod units, which has designed by Piñero and further developed by Escrick. The observation shows that it actually follows exactly the same way as the planar unit for its connection, and therefore it has the same geometric condition as planar scissor assemblies. The same assembly approach also results in the similar geometric and motion properties for tripod scissors. Therefore, it cannot reveal the specific merits of tripod scissors compared to the planar ones. As shown in the part C of the figure, a measured assembly method was formed to be able to obtain different forms and motions by using the same units. In this approach, 2 units are connected symmetrically about a plane that is determined by 3 endpoints of the units. In this case, 2 units are connected in 3 points rather than 2, and their geometric condition of foldability can be written as this equation set. And to achieve the maximum compactness, this equation must exist. This slide indicates the different motion properties when using different assembly methods and analyze the reason of their different performance. On the left image, the same tripod units are connected in different ways. The top one uses the traditional linear approach, and we can see the structure expands horizontally. And we can imagine that it will be a flat grid at the end when it's fully deployed. However, the bottom one moves curvilinearly, and the outside units are lifted above during the deployment. This curved motion can be explained using the vector-based velocity analysis as shown in the right diagram. We can see the members that are connected in the bottom unit are actually in the same plane, and therefore they rotate in the same direction during the deployment. However, the members that are connected at the top joints are not. Therefore, the velocity components in the y direction, which is this one and this one here, are mutually cancelled when calculating the resultant velocity of the top side. As a result, the structure deploys in a curved path. To examine the geometric and the motion behavior of the structure, Grasshopper for Rhino was used to build the parametric models. This image shows the script used for the modeling. The geometric parameters are listed on the left side, which are the segmental length and the kink angle of the member. This figure connects the different forms that can be achieved in fully deployed configurations when applying different segmental lengths into a 4-unit block. In most cases, the 4-unit block are fully deployed as polyhedron, except for the case L over K equals to 2, which is shown here. The structure expands as a grid. To further examine the motion property of the proposed assemblies, 4 typical examples are selected from here, and we simulated the motion of the selected cases, which is given here. We can see the motion trajectory of the nodes are recorded using the green lines, and the influence of the segmental length on the motion can be observed. The general observation reveals that when L over K is smaller than 2, the structure moves upward, just like the 2 cases on the left. When L over K equals to 2, as shown here, the structure expands horizontally. And when L over K is bigger than 2, the structure moves downward, like shown here, the last case. This table collects the steps of the deployment of the cases. The diagram on the left column shows the different member lengths used for each case. Then we apply the angulated members on this type of structures. Theta here denotes the value of the kink angle of the angulated member. And this figure shows how the kink angle changes the geometry of the structure in its fully deployed configurations. Also, we selected 3 typical cases and performed their transformation, which are shown here. According to the animation and this table, we can see that the use of angulated members does not influence much about the motion of the assembly, but it affects the deploy-to-storage ratio of the structure, as angulated members cannot close into a bundle of bars. For the motion part, the transformation of a tripod-scissor structure is actually affected by 3 factors together, namely the assembly method, member segmental length, and the kink angle. What we studied in the past slides is the basic 4-unit assembly. By connecting a number of units together following the mirrored assembly method, different forms of large-scale deployable forms can be achieved. 3 examples are shown here: the expandable arch, expandable dome, and the expandable telehandler. They're all stress-free mechanisms and have a good compactness ratio. Using this assembly method, some potential application of furniture and architecture are proposed here. For example, here is a transformable lamp, table, and a seat. In the middle is an emergency shelter, and on the right is a temporary pavilion. Lastly, I would like to thank Professor Krishnan for his insightful suggestion for this project. Thank you for your attention, and I'm open for questions.